Hello, my name is Hristov, and currently I'm an Elixir developer at Quanterall. Today I'm going to talk about consensus mechanisms, but first I want to make a short summary of the previous lectures. What is a blockchain-based system? A blockchain-based system is a classical distributed system with shared state, where all participants are geographically distributed among the world. There are two types of blockchain systems, permissioned and permissionless. Bitcoin, Ethereum are open-ended systems, they are permissionless. That means any can participate in the advancement of the blockchain. Anyone can sign transactions, verify transactions, and so on. In close-ended systems, such as Hyperledger, there are nodes which are trusted. Only they can sign and verify transactions, but every user can just request some transactions. Okay, in permissionless systems, such as Bitcoin and Ethereum, the number of nodes are expected to be large, so you can trust anybody. Anyone can run a node, and you should be prepared for some maliciousness attacks, such as cyber attack, which is you can make several identities and take bigger part in the consensus mechanism to make more votes, say, in this way. Okay. Now, what is a consensus mechanism? You can see consensus process is the method of action for network or project creators to decide on changes to the decentralized system. You can think of it as a way to make all the politicians of the parliament to agree on one opinion. But instead of discussing some political things, you can just send information from one peer to other peer, such as history of the blockchain and so on. Okay? So what is the purpose of consensus mechanism? The purpose of consensus mechanism is to allow for the secure updating of the state according to some specific state transition rules, where the right to perform the state transitions is distributed among the economic set. This economic set can be users which have the right to perform transitions by the rules of the consensus algorithm. But this economic set, these users should be securely decentralized. This means that no actor, no user or set of users can take the majority of the blockchain. Okay, these are the most famous consensus mechanisms. I'm going to talk about mostly the permissionless consensus algorithms, such as proof of work, proof of stake, least proof of stake, and delegated proof of stake. The least proof of stake and delegated proof of stake are flavors of the proof of stake, as you can see. And the last one, the Federated Byzantine Agreement, is actually a permission consensus algorithm, but it will be the spice in our tour in the world of consensus mechanisms. Okay, let's start with the most popular one, the most used, which is proof of work. Actually, as you understand it already, a proof of work is a piece of data which is difficult, costly, and time-consuming to produce, but it's very easy to verify, and which satisfies certain requirements. For example, the hash to start with 4 zeros or something like that. Producing a proof of work can be a random process with low probability, so a lot of trial and error is needed on average before a valid proof is produced. This is algorithm used by Bitcoin. It's used by the miners. I think Nedeltru explained how. It is used by Eternity too. We are using Cook cycle proof of work. We can discuss that later. What are the steps in the proof of work? The steps, first, the transactions are bundled together into what we call a block. Then miners verify the transactions within each block are legitimate. To do so, miners should solve a mathematical puzzle known as proof of work. A reward is given to the first miner who solves this problem, and then verified transactions are stored in the public blockchain. What is so special with this mathematical puzzle? Well, it's asymmetrical. It's very hard to solve, but very easy to verify. The algorithm includes hashing, as you know. First, here is the graphic. We take the latest block, which is block n, and the current block we are trying to find, which is block n plus 1, which has all the elements from block n. But it doesn't have only the nonce. The nonce is random number which is concatenated with the block n and the transactions from block n plus 1, which is the current block, and we concatenate the nonce. Then we run all this into a cryptographic hash function, and we receive a hash value. We check if it's less than the threshold, also called difficulty or target. This is the way Bitcoin keeps the consistent time of mining a block by regulating this threshold. If it's not less than the threshold, we change the nonce and try again. But if it's less than the threshold, we have a valid proof of work. Okay. I'm gonna talk about the different theoretical attacks that can happen. But first, I should explain what is double spending and what's blockchain fork. Okay, first the double spending. Imagine you have to buy coffee. And this is the seller A. And I make him a transaction for 1 Bitcoin. But at the same time, I make a transaction to seller B with the same Bitcoin. And or I can do this to myself. So only one of the transactions will be verified as valid. The other one will be rejected. So there's a 50% chance of me getting my money back. Okay. So blockchain fork. Imagine two nodes, two miners to find a block at exact same time. Then the fork appears. So how to decide which fork is the real fork, the trusted? Everyone decides to which block, vote on which block is the real, and the longest chain is the true chain. Okay. So this is the attack vectors: race attack, Finney attack, vector 76 attack, alternative history attack, and majority attack. The race attack can happen if the merchant, I will call it that way, if the merchant accepts a transaction before it's confirmed. Then I make him a transaction, and I make transactions to myself with the exact same money. So only the one of the transactions will be accepted, and I have a 50% chance to get my money back and to not give him money. But this is only if he accepts a transactions before it's confirmed. The Fini attack is a little bit different. You have to mine a block in order to perform this attack. You first mine a block which has transactions to yourself. And when you mine the block, you do not broadcast it. You keep it for yourself. Then you make a transaction to the merchant, and if he accepts it before it's confirmed, then he's on the net. So you broadcast the block, and transactions made to him gets invalid. So he does not receive any money, and you have your money back. The next attack is Vector 76, which is a mix of the race and the Fini attack. More interesting is alternative history attack. This attack can happen even if the merchant does not accept the transactions before it's confirmed. But this is attack with very low probability because you have to outmine the other mining nodes. You should you should fork the whole chain. You should make your fork and outmine the other chain, which is nearly impossible. And there's the majority attack, which is almost the same as the alternative history attack. It's also called 51% attack. This means you have to have at least 51% of the mining power, which is very, very expensive, and it's nearly impossible. Yeah, with 51% of hashing power, you could imagine what you could do. You can just outmine everyone and make your own transactions, and your fork will always be the true chain. Okay, let's continue with the proof of stake. In proof of stake, public blockchains, example, Ethereum's upcoming Casper implementation, a set of validators take turns proposing and voting on the next block, and the weight is and the weight depends on your stake, the size of its deposit. In other words, the money you have. Significant advantages include security, reduced risk of centralization, and energy efficiency. Here's how it's done. Validator A has 10% of the stake of the whole network. Validator B has 50% of the stake, and validator C has 40% of the stake. And here are the blocks. The highest chance to validate a block, to become a validator, has validator B, because his stake is the biggest from the others. And if he validates block 4, it receives the transactions reward of 0.06 gold. It is simple. You can imagine this as you're going to vote, and instead of ballot, you give money. If I give more money, I will be a president, for example. But this is not, but the creators of proof of stake have think about that. The stake is measured for 30 days. And every 30 days there are new elections and new stakers. Because the stake is measured for 30 days. When the 30 days expire, your balance becomes zero again. Your stake becomes zero again, not your balance. But this money cannot be included in the stake anymore. Once they have been in your stake, they can't be again the next month. What's the benefits of proof of stake? There's no need to consume large quantities of electricity because it's not a computational hard like proof of work algorithm, for example. There's not as much need to issue as many new coins because the money needed for proof of work mining includes taxes for electricity and so on, and to stimulate the people to involve there, they're producing more and many new coins. There's no need here. Also, it discourages centralized cartels and reduces centralization risks. Okay. Now for the nothing at stake problem, some problem that can occur in the proof of stake algorithm. Let's think of fork A. This is a blockchain fork. Let's think of fork A to be the true node, the true fork, and the node B to be some malicious fork. Okay, if I'm a validator, I can just vote on A, vote on B, and take a reward of 1. If I vote only on the good fork, the true fork, I will take only 0.9. But if I vote on the malicious fork, I will take 0.1. But if I vote on both, I'll get 1. There's no penalties for voting for the both forks. Well, there's some solutions to this, and I will present them to you. If I vote on A, I will be given 0.9. If I vote on B, I will get 0.1. And if I split the vote between both, I will get only the half of A and half of B. There's some, and here is the solution with some penalty. If I vote on A, I take 0.9. If I vote on B, I take 0.1. But if I vote on both, I take 0.1 plus 0.9, and this is the penalty of -5, and I lose money. This encourages me to vote only for one of the forks. And this is maybe the best solution. This encourages me to vote only for the right fork. If I vote on A, I take 0.9. If I vote on B, I take the fee from B, 0.1, minus the fee from fork A, multiplied by 5. So I'll have minus. But if I vote on both, I will still lose less if I vote on the malicious node. This is because if I vote on only the malicious node, this malicious fork can win the battle between the right fork, which is A, and B. If the malicious win, then the fraud will be performed, will happen. if I vote on both, I'm keeping the chances equal, as you see. And the best case is to vote on the right one, the truth no, the truth false. Okay, let's look at some flavors of the proof of stake. This is least proof of stake. Least proof of stakes achieves participating of all stakers, no matter how many money they have in their accounts, to lease their balances to the staking nodes, to the most wealthy people in the network. The leased funds remain in the full control of the holder and can be moved or spent at any time, at which point the lease ends. Leased coins increase the weight of the staking node, increasing its chances of being allowed to add block of transactions to the blockchain. And if the staking node validates a block, the reward is split between him and the nodes who leased him their money. So let's see. These are little stakeholders. They have no chance of validating block all by themselves. The chance is little. You can think of it as if you have low hash rate in proof of work, your chance of mining a block is very little, right? Okay, and imagine stakeholder 1, stakeholder 2, and stakeholder 3 lease their stakes to validator 1, and now his weight is the 40% of all the stake in the network. Yeah, that's the most important for the least proof of stake. One of the first implemented the least proof of stake are waves. Their miners run nodes to secure the waves network and are rewarded with fees. Their rewards depend on the amount of waves they use to mine. The more waves, the greater rewards. Regular users can lease their waves to miners from the light plan, thereby increasing the waves they can use. And in the end, the miner shares the rewards without giving up control of their waves. Now, delegated proof of stake. This is approach taken by BitShares and a number of other platforms. With delegated proof of stake, coin holders use their balances to elect a list of nodes that will have the opportunity to stake blocks of new transactions and add them to the blockchain. This list of nodes, every node is called a witness. Every votes for witness, and witnesses are producing blocks. And the top n witnesses who produce a block receive a reward. If they have a short time interval for each witness to produce a block. If he can't produce for that time, around 2 seconds, then he gets no reward. That's it for the delegated proof of stake. And the last one, and the spice. This is just to see how different is the permissioned blockchain system, different from the permissionless. This is federated Byzantine agreement. This is a consensus mechanism which assumes participants know of other participants and can distinguish which it considers important. The requesting node waits for his important nodes, which are known for him, to agree on the transactions. His important nodes wait their important nodes to approve, and sooner or later there will be a consensus. That's the way the federated Byzantine agreement works in short. Okay, thank you for the attention. You can find me at my Quanterall email, and don't forget to follow Eternity Project. Thank you. Any questions?
I have a question. What will happen if in, let's say, Bitcoin network, there are no transactions for a considerable long period of time, let's say for 1 month. For 1 month, there is no single transaction in Bitcoin. What will happen?
I can only predict what will happen, but I do not know for sure.
It is software. There are clear rules how it operates. You know all these rules. What will happen?
Time doesn't matter.
No new blocks will be generated.
Yeah, there's no new blocks generated.
So the miners can create no transactions.
The Bitcoin network will be on idle state and can go out of it at any time.
From my point, 1 second, 1 month, 1 year, doesn't matter. The miners will lose interest.
Actually,
No, it's not true.
there will be empty
they will
blocks
mine
mined.
empty blocks, so they will get the reward. The only problem is if the reward will worth something. So they will get the coins, but the value, we don't know what will be.
From where these empty blocks will appear? Who will generate them in order
The
to
miners.
spread? By themselves.
Yeah, at the moment you can see the blockchain there.
To exchange bitcoins.
Even at the moment there are a lot of empty blocks, so it's not a problem. We already have such blocks.
Yeah, there will be empty blocks. If a miner, as I said, the target difficulty, which is determined by Bitcoin, they decide to mine block once each 10 minutes, for example. And whether there will be transaction requests or not, a block will be mined, no matter if it's empty or not. The miner will receive his reward.
Exactly like in the beginning.